Everybody, welcome to the September 2024 indoor meeting of the Raleigh Astronomy Club. Stefan, would you like them to wait until we're at the end of your presentation to ask questions, or would you like them to raise their hand and interrupt? Okay, we'll just wait till the end. Keep your questions till the end. What, Frank? Either one. Okay. Okay, guys. I want to keep making sure everybody's safe in here. So for our safety slide, wow, these are really delayed. Can we identify some room hazards for everybody? We got cables running behind the projector, network cables and power cables. We've got chairs with bags beside them. We've got, the lights are down low. So just watch where you're going. Anybody CPR trained in here, please raise your hand. We got Bhupinder, we got Mike. Nate. Okay. So who is my designated emergency caller? I need somebody to dial 911 if somebody passes out, specifically me. Okay. Yeah, you. You do have a cell phone, right? Okay. That would be my luck. Okay, fire equipment. There's a fire extinguisher on this back wall on the left hand side just before entering that room. If you're online, please make sure that you don't have things that can trip you and that you're got somebody that knows where you are and what you're doing so that you can stay safe. For those of us in the building, you're in this A-level conference room right here, and your emergency exits are out that door and out that door and up the stairs. Please don't use the elevator. Okay, Ms. Secretary, announcements. I'm sorry.
Hi. The books are in. If you ordered one and would like to pick it up, I have them here. I do not have the log books. We actually cleared out Peter's stock and he had to reorder them. They're not in yet, but they should be available soon. I'm going to be at Staunton River next week. I'll be here at whatever. So if you are on Zoom and you want to pick it up, just let me know. Thank you.
Okay. All right. So tonight, we're going to stop right here for a few minutes, and we're going to vote on officers at this time instead of at the end. Your officer nominations are the following. I don't think I need to read through them. It's exactly who you have right now. And we need a show of hands and people on Zoom to vote. How do you want them to vote on Zoom? Can you please vote in the chat? Would you like just a type of +1 if you're okay with the officer nominations? And we'll wait a few seconds and then we'll just do, you want to show of hands? Okay. And remember, you got Steve Blake. He's already, and Izzo, both of them have already voted. Yeah, this is members only, kind of like the jacket. Correct. We're still missing a co-chair. So could I get in the room? Could I please get a show of hands? Naveen, will you count, please? And I'll count as well. Or all in favor? That's what I got. 29, so that carries. Yay, that's done. I wish. Jim, I wish. Okay. Next thing we're going to do is we're going to vote on budget ratification. If you didn't get a budget, and it looks like nobody did because they're up under here, here's your budget that we've got. I'll be more than happy for everybody to set it up here. But the problem is nobody's looked at it now. So it was, but just in case, if you didn't get one that's printed out, please get out your glasses because you're going to look at this screen here. I don't think you do. So we're going to vote on the budget. This is our first year of having a budget written like this. I'm sure it's a continuing learning curve. Naveen, would you like to speak on this at all? Okay. So we're just voting. Yeah. I mean, if you got any questions online, please post them. If you got any questions in the room, raise your hand. Mike? I thought so. Did you not? I think there's a couple there. It feels like a couple there. Anybody else want any? I mean, you make airplanes with them too. Okay. So we need to vote on ratification of this. Is that a correct statement? Okay. Same thing we just did. Can we get plus ones in the chat? And can we show a vote in here by raising your hand? So for ratification of the budget, please be a member. Please raise your hand if you're okay with it. I got 18, and you got Steve, and you got Izzo. Okay, so you got 28, so that carries. Okay, so now the fun starts. Okay, Steve Blake is not here tonight, so I'm going to run through these really quick. So Staunton River, just want to share with everybody that's happening. I bet you knew that. I thought you did. Okay, so October 4th, October 30th, first Fridays in the Willard. I'm just going to shoot through these really quick, guys, because you guys can speed read faster than I can do it. Stargazing, Prairie Ridge. I was just going to make a note on the one for November 23rd, where that's a joint event with Moorhead Planetarium. STEM night, woo! First Fridays. Anna, are you going to be in town on the 6th? Okay, it's canceled. I'm sorry. If she's ever here, it rains, it seems like. All right, Willard Laptop on the 18th again. I'm sorry to play. So the Raleigh Astronomy Club does a barbecue once a year now, and ours is coming up on the 12th of October. Please note the last line here. No, I don't. Do I have it? Oh, there you go. Deadline for sign up tomorrow, midnight. If you don't sign up, sorry. Yeah. Tonight, we're going to go to the Alamo Draft House after the meeting. If anybody would like to go, do I need a show of hands, Naveen? We can go wherever you guys want. I have to. Okay, then let's go to somewhere else. Okay. So I don't know. Are we going to? Do you guys want to change it? I got that. No, I don't think anybody else minds if you do. So I guess we'll go to Sammy's tonight. So if you guys don't know this, December the 11th, an asteroid passed directly in front of Betelgeuse. Fortunately, Winona Ryder was able to get it back.
Betelgeuse.
It's showtime.
So tonight's presentation is Stefan. Trying to be a goofball. Sorry, Stefan. So for those of you that don't know, Stefan is an active participant in citizen science within the Unistellar Network, contributing to research that has led to several co-authored scientific papers on exoplanets and asteroids. He is committed to outreach, aiming to make the science accessible to the broader audience. Professionally, he works as a software engineer at Zendesk, a provider of online customer service tools. With that, Stefan, it's all you. We have to transfer your screen.
Can you hear me now?
Yep.
That worked? Excellent. Yeah, yeah, thanks for having me. Kind of excited to be talking about some more about Betelgeuse. I will only say it at maximum twice. Um, this is actually a presentation I gave in January at the astronomy days, like next door. And like I thought I'll just give it again. So yeah, today I'm gonna be talking about Betelgeuse. The joke has already been taken, maybe. Not him. Yeah, I mean, isn't it fitting? It's almost Halloween. Yeah, so I'm talking about the prominent red star and the Orion constellation that I would think we all know. And there's a lot of speculation that it might actually be the next supernova in our galaxy to explode. So there's just been a lot of excited speculation over, especially last year, about like unusual brightness variations that the star has been exhibiting. And there's actually some talk about that it may supernova, instead of exploding, within the next 100,000 years, that it might actually be within tens of years. So there's lots of talk, right? So the name, I'm going to go a little bit into history. Like the name comes from Arabic, Betelgeuse. I'm probably butchering that completely, so apologies. It's actually, the name is actually a really bad transliteration, French letter transliteration of an Arabic name, the Latin, like Western name. Literally, that means the hand of Yalsa, the central one. So it's like, or in one translation, the armpit of the giant. So it's like, I think everybody looked at this and thought, like, a lot of different cultures are like, well, it sort of looks like a guy, like a person. So everybody kind of associates that with a giant or or hunter as a Western. There are also various pronunciations of the name, and what I've read, and people who've been around astronomy longer that I have, that the name Betelgeuse was kind of a result of the movie in 1989. The standardization on that pronunciation, as opposed to Betelgeuse or something different. But anyway, that's what I read. So yeah, so in Western lore, Betelgeuse is the right shoulder of Orion, right? The great hunter of Greek mythology, who was sent up to into the heavens because he wanted to kill every animal in the world and pissed off Olympus, and he was sent up into the heavens as a constellation, along with the scorpion that killed him. And he's still kind of hunting Taurus, like he's right next to Taurus, so he hasn't really learned his lesson. Moving on to the Aborigines. So there's like an ancient oral tradition from the Aborigines. And you can kind of see, like, this is like everything upside down. Like instead of Betelgeuse being in the top right, top left, he's in the bottom right, because it's Australia. So there's an Australian like an Aboriginal story, oral tradition that says that, which tells of Niruna, who's represented as Orion, same stars, also a hunter, who is pretty vain, and is after the Eugalia sisters, which are the Pleiades. Interestingly, also sisters. So, but they don't really like him, right? They're kind of timid and shy. So their sister, their older sister, Kambuguta, the Hyades cluster, fights him, right? She protects him. And how do they fight, right? Like they have fire magic. There's Betelgeuse and Aldebaran. And they're just sort of, going at each other. And so what happens is that she hits Betelgeuse, or he hits Nerunia, and his fire magic kind of briefly dies out. And then it comes back. But she isn't able to replenish her own magic quickly enough. So she sends a group of dingo puppies between the two, which then surprises him again, and his magic dies again, right? So it just sort of keeps on going on and on and on and on. And why am I telling you this? The reason that stories like this, talking about like the fire, lighting up, dying, is that it's actually the case that Betelgeuse and Aldebaran are variable stars, right? Like Betelgeuse varies in 1 magnitude every 400 days. Aldebaran 0.2 magnitudes at very irregular intervals, right? So the story was basically like she wasn't able to keep up because it didn't flicker fast enough. It didn't go bright and so on quickly enough. So this actually, it's kind of an indication that, which is going to be kind of important later on. Betelgeuse is a variable star. So Betelgeuse is a so-called red supergiant, right? It's visible in both hemispheres. It's like one of the most well-known stars. And its color is very different to all the others, right? Like the blue ones, like that's Rigel down here in the corner. So Betelgeuse is called Alpha Orionis. Rigel is Beta Orionis. The naming comes from a naming scheme that a cartographer, German lawyer and cartographer Johann Bayer put in the star atlas that he published in 1603. And he labeled the stars based on like an order of brightness, right? So alpha is the brightest, beta is the second brightest, gamma is the third brightest, and so on and so on. But turns out that Rigel is actually brighter than Betelgeuse right now, right? So that means that either Rigel has gotten brighter since the 1600s, or Betelgeuse has gotten dimmer. So there's sort of another piece of evidence, right, that something might be going on here. So Betelgeuse is big, 550 light years away from Earth, and an estimated of just 8 million years old. Compare that to the sun's 4.5 billion years, right? It's also 14 to 19 times more massive than the sun, and 760 to over 1,000 times larger, right? So if Betelgeuse was at the center of the solar system, it will go all the way to beyond the orbit of Jupiter. So probably not. Wouldn't be good for us. This is actually an actual image with the solar system superimposed. This is like a Hubble telescope image of Betelgeuse, of the disk. Like it's so big that we can actually take a picture of it. It's not just a little point dot in the sky. How big? Well, here's a comparison, right? Like sun is right there, and Betelgeuse is right there. So it's huge. The thing about this picture is that I wanted to point out is that stars that big don't look like that. Like they're more like puffy clouds of gas. They're not like balls. But it's still a good size comparison, right? Like they're very fluffy, like this. So So this is like if you actually take a picture of the star and blank out the star, you can see all the gas that's around the star that that you normally can't see because it's just the star just outshines it. And this is like basically Betelgeuse is giving off matter. Like it's really unstable. It's like this cloud of this star that can't even hold on to its outer layers. So yeah, very interesting. So because of some unknown event in the past, Betelgeuse is actually moving through space quite rapidly. So here, up here is Betelgeuse, right? Orion constellation. So this is like an animation of, oh, this isn't updating as quickly. Anyway, it's actually a smooth animation on my screen. So this is like a animation of Orion constellation over the next 450,000 years. And you can see how Betelgeuse kind of starts moving off the frame after about 100,000 years. But that, if you go back, like that also means it's actually been born somewhere completely different from where it is now. So it's high proper motion, but obviously not as high as some stars you can actually see over time. Like it's still relatively slow, but it's moving, relatively quickly as far as stars go. And one interesting fact about that, about it actually moving so fast, is so you actually, in order to determine the age of a star, or even the life cycle stage, one way to do that, one big input to that, is the original mass. Like how big was it when it was born? And normally, if a star doesn't move, you still have all the gas around it. You can measure. You can be like, oh, there's this much stuff around the star that came from the star, so we can kind of say and add that to the mass we can determine for the star itself. Because Betelgeuse moves so quickly, it's just losing all this material, and we can't actually figure out how big it was because we don't know where it left all this material, right? We don't know where it came from. So that makes that bit difficult. So before I get into what happened there? Somebody's drawing. Uh-huh.
And then click more on the toolbar.
Okay.
And then click
Disable annotation. All right. Cool. Excellent. Thank you. Always learn something new. So before I get into some of the controversy, I wanted to kind of lay some context about the life cycle of stars. Right, so stars are born like people, go through a life cycle, born in nebulas, live through their main adult life as they fuse hydrogen into helium, like our sun's doing right now. And then as they run out of fuel, they swell up and eventually die. So a star like our sun, so there are different paths, right? Like you can have, you start off with a cloud, and then you get a protostar, open cluster, and you have different masses of it. So the mass of the star actually determines a lot of what it looks like and how long it'll live. So for a star like our sun, like a low mass star, less than 8 times the mass of the sun, it'll turn into a red giant, swell up, and then eventually you end up with it sheds its outside layers, and you end up with a white dwarf at the end. But I'm gonna just mention this just for context. But I could give a presentation about just all this stuff. So I'm going to just focus on massive stars like Betelgeuse. So Betelgeuse probably started out as a blue giant. It was blue in the beginning. Then turns, these kinds of stars turn into these red supergiants, explode in a supernova, and then either you end up with a neutron star, which actually is a pulsar, at the end, or a black hole if they're really, really heavy. Again, also all the function of mass. And then you get nebula as well as a remnant. This is the Crab Nebula. So what happens exactly when a star dies, right? Let's talk a little bit about what happens when they're born, or when they, kind of live their lives. So stars form from clouds of hydrogen gas, right? That contracts under its own gravity. Once the pressure is so high, is high enough, hydrogen starts to fuse into helium, and the star ignites. And what that does is it's sort of like you get the force of gravity collapsing the star, and then eventually fusion igniting and causing pressure like a balloon to blow the star back up and keep it from collapsing, right? So it's this what's called a hydrostatic equilibrium, like a balloon, right? It just keeps the star, in balance. Turns out it's not entirely stable. So stars actually, especially large stars, kind of pulsate a little bit. They get, when they, like in one direction, they might get bigger and then get brighter because it's an increased, like, bigger surface area. And then they get smaller and brighter. So that's like the source of a lot of variable stars. And so especially at later stages that happens. And that's also what, causes like the 400-day cycle that the Aborigines built their story around. Once the hydrogen runs out, like the star starts to contract again. And so it, like, hydrogen runs out, fire goes out, it starts to, like, gravity kind of pulls the star together. And then at some point, pressure is high enough that now instead of fusing hydrogen to helium, fuses helium to carbon. And so that cycle goes on and on and on. And I'm talking about like big stars, like stars like our sun. It's just a little different. But as you go from carbon to neon, neon to oxygen, silicon to iron, and at iron it actually stops. Like you get this inert iron core. So what's interesting is that the stages, the time these stages last, right? Like hydrogen fusion for a big star like that, 7 million years. Helium, 500,000 years, right? And then once you get to oxygen, 6 months. Silicon, 1 day, right? Like it goes quickly. And you get into sort of somewhat human timescales once you get to fusing carbon. So a lot of people are talking about, like, well, has it started to fuse carbon yet? I'll get into that in a little bit. So we believe that Betelgeuse right now is already significant in part through helium fusion, right? So it's in this like 500,000 years where it fuses helium into carbon. So in the end, the core of the star looks like this, right? Like you have the star that you can see on the outside, and then there's this little core, which is like kind of a layer cake of some non-fusing hydrogen still fusing, helium is fusing, carbon fusing, and then there's this inert iron core. And but because there's no more fusion happening at the center of the star, because it's iron, there's nothing to prevent the star from collapsing even further. Was there a question? Okay. There's no back pressure. Yeah, exactly. It's really kind of interesting. It's all about pressure. once it gets to like quantum pressure at some point as well. So, and yeah, so there's nothing that holds it back, right? So the star eventually just collapses, which then causes a shock wave that tears the star apart. That's a supernova explosion. And but what's interesting is during the last few milliseconds of that collapse, that should have been bigger. The pressure becomes so high that the fusion actually continues, right? In a few milliseconds, you get all the other elements of the periodic table, right? So that's why people are saying like we are all star stuff, right? So what does that look like? So that's a simulation of a supernova, right? And it's actually, you might recognize it. It's the supernova that produced the Crab Nebula in Taurus, which, again, historical analysis is actually based on Chinese records, could be dated to the year 1054. Because it's really relatively nearby, you can actually still see it expand, right? Like year over year, if you take pictures, you see it actually changing and getting bigger. And at the center of the nebula, there's a neutron star, which is basically a ball of mass that's just neutrons. Like that's about as massive, as dense as ordinary matter can get. And so that object is just 12 miles in diameter and so dense that a teaspoon would weigh like 10 million tons of that material. Yeah, and obviously that's basically what will also happen to Betelgeuse in the end, right? That's what's going to be left, plus a really pretty nebula. There's another example, the Cygnus loop, also a supernova remnant that happened 5,000 to 8,000 years ago, and in Cygnus. And it's 1,500 light years away. And it's so large that parts of it have their own names, right? Like there's a Veil Nebula and a bunch of other things. This is one that happened just last year. It's a supernova in the Pinwheel Galaxy, M101. And so, I mean, obviously, right there, it's flashing. So this is like two pictures I actually took with my own scope. One the year before, and then in last year, and you can clearly see the difference, right? And that took months to dissipate. So here's like a light curve of the brightness shooting up and then slowly dissipating of this supernova, right? So back to Betelgeuse. So how do we know what development stage Betelgeuse is currently in and how old is it? Right. So this is what's called the Hertzsprung-Russell diagram. Right. So it shows the distribution of all stars. It's based on the distribution of all stars in the Milky Way or in the night sky by temperature, surface temperature, and brightness. Right. So the temperature determines the color. Right. So a star that's really hot is blue. A star that's really dim is it's reddish, kind of like a light bulb color temperature, right? And so obviously bright stars are also very hot, and dim stars are relatively cool, and the sun is sort of right there somewhere, right in the middle, very ordinary yellow. And this is what's called the main sequence, right? And of stars, where stars kind of are, spend most of their life. Stars that are really, really big don't last very long, right? They last like millions of years. Yellow star like our sun, billions. And then these like very dim red stars, most of them are still around. Like none of them has actually died since the universe, came about. So, and then what happens to these, right? Like as a star goes through these changes while it's dying, it's leaving the main sequence, right? It swells up. So examples of a sunlight star would be Arcturus or Aldebaran or Pollux that used to be the size of the sun, but are in the process of going through kind of the last stages. Then there are supergiants, which is where Betelgeuse is right there. So they actually started out blue and very, very large, and then are cooling down as they get bigger, right? The brightness doesn't change much, but they're getting cooler, and because they're cooler, they turn more red in color. So that's why Betelgeuse is red. And what tells us, if you just look at the brightness as a function of the surface temperature, you can almost tell, like, where are they, right? And so a star like Betelgeuse spends about 8 million as a blue main sequence star, and then it goes through this yellow phase that lasts just 10,000 years and spends the rest of its life as a red supergiant for up to like a million years. So that also means that Betelgeuse's surface temperature is actually cooler than the sun. It's huge, but it's not actually that hot. So there was like a recent survey of historical records that suggests that it may have actually appeared yellow just 2,000 years ago, which we, like, looking at that diagram, means that it's sort of halfway through this leaving the main sequence. So there was like a quote from like a Chinese court astronomer, Sima Quan, who said that Betelgeuse's white light, he said white is like Sirius, red like Antares, yellow like Betelgeuse, blue like Bellatrix. And Bellatrix is actually another one of those blue stars in the Orion constellation, right? So he had Bellatrix and Betelgeuse right next to it, and he's like, well, Betelgeuse is yellow. So that's a pretty big, indication. Then Hyginus, like a Roman scholar, said that Betelgeuse is similar in color to Saturn. And if you looked at Saturn, right, it's not red. It's sort of this like, I don't know, salmon color, orangish type color, right? And then the Greek polymath Ptolemy made a list of red stars in the sky, but did not actually include Betelgeuse. Right? And then in other writings, he described the color as something called chiros, which could mean anything from pale yellow to reddish, but definitely not red, right? It's sort of like in between. So if this is true, right, that means that early human civilization was pretty much already around when Betelgeuse evolved from blue main sequence star into this, yellow supergiant phase of end of life, which I think is pretty exciting, right? So moving on, there's a last year there was this event called the Great Dimming, which in 2019 Betelgeuse experienced an event, right? It was 2019. And what happened was that its brightness dropped dramatically to just 30% of its usual brightness within the course of a year. So this is like the brightness history of Betelgeuse 2017, 2018, 2019. You can see this like massive drop. This is like an animation of what that looked like, right, in 2019. Like, again, pictures of the actual disk of the star. So the sudden dimming of the star, that could be an indicator that the star is in the final stages of contraction prior to exploding. And that has led to a lot of excited speculation. So sounds like people really want this thing, to blow. And yeah, there was so many of these. I'm like, I gotta stop finding screenshotting stuff. But it turns out that it was a false alarm. By April 2020, things just returned right back to normal. So yeah, you just gotta kind of. It was just an outlier. And it's back to its regular 400 day pulsations period, right? So what happened? Turns out that Betelgeuse had belched off like a big piece of material that, as it cooled, formed into like a dust cloud. That happened to, dust cloud cools down, dust cloud. It moved right in front of the star as viewed from Earth. And that is what resulted in this dimming as viewed from here, right? Like it had nothing to do with the star itself. It was just a bunch of dust that happened. Our sun sometimes does that too. There are something called, coronal mass ejections. Kind of similar thing, but fortunately the ones in the sun aren't this massive and violent. So yeah, this is like a series of images that show this behavior as well. You can see kind of the dust cloud moving out of the way, and then it's back to its normal brightness. So moving on. So as I mentioned earlier, right, like if you look at the carbon burning phase where carbon starts fusing into oxygen, we're in the hundreds of years time span of supernova. But the hard part of determining what's actually happening inside the star is that you can't see it. It all happens in the core. Like all we can see is this big ball of gas around it that has hydrogen, right? And so there's like a lot of significant uncertainty about its mass and age, like I mentioned before, because it's moving so fast through space. But there was a recent research preprint that that a recent increase in the rate of pulsations of 400 days move to quicker, that might actually indicate that the carbon burning stage has started. And then once that's completed, it will go supernova in tens of years. And you can imagine the excitement that has caused. So this is like the paper, right? Yeah, very excited people. Yes.
So is there any consistent observation of Betelgeuse at the spectral level so that we'll have a record of its last 10 or 20 years?
Yeah, I mean,
kind of sporadic.
Betelgeuse is like, I would say, watched every single day, right? Like there's the AAVSO, American Association of Variable Star Observers, that is kind of the clearinghouse for collecting all that data. So anybody can point their scope,
Yeah, maybe I should restate that.
Mm-hmm.
Is there any major professional astronomical observation, its spectral signature?
Mm-hmm.
So,
spectrum as opposed to filters.
as opposed to basic visual observation,
Mm-hmm.
or even photometric observation.
That's a good question. I don't know. Probably. I would also say that using photometry is probably enough to to do that. But yeah, and we can talk about this afterwards. So yeah, so people were so excited that I kind of missed the conclusion of that paper. Later on, like the authors clarified that they predict that the supernova will happen in less than a few hundred years. But that's what they were saying. But what people were reading is some quote later on that said something about tens of years. But that was like, well, once it's done with the hundreds of years, then it will be just tens of years. But yeah, so I don't know. But in the end, people also pointed out that they also use an incorrect radius as an input of the star as an input to the model. So even that may not be correct. So it's science, right? So in the end, who knows? So there's actually another thing that just happened, but maybe I'll skip over that. I think we're sort of running short on time. That actually happened last year, just last month. That there might actually be a binary companion that could maybe explain some of the variations and there's a long cycle as well beyond the 400 years. So anyway, but we don't know when it will go supernova. We just know it'll be an amazing spectacle. Right? With this like big bright, spectacle in the sky. And when it will occur, it will max out near -10th magnitude as seen from Earth. Yeah. And that's more than 100 times brighter than Venus. Or, yeah, exactly. Almost as bright as the moon. Yeah. And could potentially even be visible during the day.
We have a question on Zoom.
Mhm.
It says, since Betelgeuse is estimated 400 to 600 light years away, is it possible it has already gone supernova?
Yeah, that depends on your point of reference. Yes. But that's not what we're talking about, right? Absolutely, yeah. Good question, though. Yeah, anyway, that was the end of my presentation. I don't know how we're doing on time, but is there time for questions or? Okay, cool.
Thank you, Stefan, for the
Mhm.
presentation.
Yeah.
Could you go back to the slide where you show the timelines of basically when it's burning, or it's actually
Burning
going
what?
through the fusion processes?
This one.
Okay, so all right, that's what we're referring to. If it's started the carbon fusing
That's right,
process,
yeah,
it's 600
exactly.
years to get to that.
Yeah, exactly. So we have very good models of what a star, as long as you know the mass of the star and all the parameters, we can predict, how long these stages will take. And this is, again, I put a note there that says that's for a star the size of Betelgeuse, right? Like the sun, different. Anything else?
I bet a lot of those. I bet a lot of those pictures up there were simply hydrogen alpha pictures of the sun, our own sun.
Oh, you mean the comparison there?
Yeah.
Yeah. It's cheating.
Some pretty striking images, especially if you're playing around with the contrast control on the camera.
Yeah, I don't know where these came from.
So, Stefan, back to your timeline over there. So, if it's in the carbon burning phase,
Yeah.
and I think the gentleman over here was asking pretty much the same question. The spectra coming off that would indicate that it's a carbon
No,
star.
it wouldn't.
It wouldn't,
because
okay, so that's why.
So if you look at the next slide here, right, what you see is the surface, and the surface is all hydrogen.
Or so you're saying that the carbon hasn't yet made it to the surface then?
Yeah, it's because it's in the center here, right? I mean, so what happens at the carbon will only make it to the surface once it explodes, right? And actually, fusion, even in the sun, right, happens at the center, and it'll take I forgot, thousands of years at least for that radiation in the center to actually make it to the surface. So it's a really slow process. And once it's at the surface, it's visible light. The center will be gamma rays, and then you don't see the gamma rays, fortunately. Gamma radiation, it sort of is this process of like, molecule atoms being excited and shedding like energy, like photons, and then it's just,
I think it's about 100 years for a photon.
100 years. Yeah.
From core out.
Yeah. Forgot what the number was.
It's just bouncing back and forth.
Exactly. And it sort of spreads out, and then the energy goes down, and you end up with visible light rather than, high energy gamma. Yeah.
So then what you're saying is that. Sorry.
Yeah.
So what you're saying is basically is that once it does begin fusing carbon, there's going to take, I don't know, 100 or to 1,000 years for it really, because it's so dense in there, to kind of bounce around before it actually makes it to the photosphere. We can actually see that spectrum.
Yeah. I mean, it just, so what happens, right, is that as it's burning, fusing carbon, right, like that still props the star up, and you don't see any kind of signature of that on the outside.
Oh, that's a good point.
Yeah. Because it's still, gamma rays, like it's
yeah.
fusion, just more energy and higher energy, more of it.
Hey man, by the way, excellent presentation, by the way.
Thank you.